Good morning, everyone. We're going to discuss about linear programming. Linear inequalities. Inequality tells us about the relative size of two values. We call these things inequalities because they are not the same or not equal. The symbol is read as is less than or as read as greater than. We also have symbol like is less than or equal and is greater than or equal to, respectively, are also used.
Properties of inequalities. The following are the properties of inequalities which can use in dealing with problems in inequalities. Number 1. Addition property of inequality or API. For any real numbers a, b, and c, if a is less than b, then a plus c is less than b plus c, and if a greater than b, then a plus c greater than b plus c. Number 2. Multiplication property of inequalities or MPI. Number 2. Multiplication property of inequality or MPI. Let a, b, and c be real numbers. If a is greater than b, then ac is greater than bc for every positive number c. If a is greater than b, then ac is less than bc for every negative number c. If a is less than b, then ac is less than bc for every positive number c. If a is less than b, then ac is greater than bc for every negative number.
Trichotomy property means that when you are comparing two numbers, one of the following must be true. The first number is bigger than the second number. The first number is smaller than the second number, or the two numbers are equal. Example, given two numbers, 5 and 7. 5 is less than 7. 5 is equal to 7. 5 is greater than 7. When we say transitive, the transitive property of inequalities. If a, b, and c are the real numbers, then the transitive property of inequality is given as if a less than b and b less than c, then a less than c transitive property can also be applied to other inequalities, such as greater than, is less than or equal to, and is greater than or equal to.
Geometry of linear programming. Linear optimization or linear programming, Bertsimar 2017, is a subfield of much broader optimization, field called convex optimization. Hyperplanes and half spaces. Definition 1. Let A be a non-zero in Rn, and let B be a scalar. A hyperplane is an equation, whereas a half space is an inequality. It's a linear equation in two-dimensional space with coordinates x1 and x2. This is also known as line equation. So a hyperplane in two-dimensional space is line. Similarly, in three dimensions, is a linear equation and it is known as plane. In more dimension than 3, the geometric object constructed by a linear equation is called hyperplane.
Half space is similar to hyperplane, but it covers the area on the one side of a hyperplane. In the above picture, the side red dots that are in is a half space, and the side green dots that are in is another half space, and they are separated by hyperplane. In other words, hyperplane is the boundary of a corresponding half space.
Convex sets. A convex set is a set of points such that given any 2 points A, B, in that set, the line AB joining them lies entirely within that set. That is why left plot is convex and the right plot is non-convex.
Linear programming problem. A linear programming problem, or LP problem, winner 2016, into unknown x and y is one in which we are find the maximum or minimum value of a linear expression ax plus by, called the objective function, subject to a number of linear constraints of the form cx plus dy, less than or equal to e or cx plus dy, greater than or equal e. The solution set of the collection of constraints is called the feasible region of the LP problem. The largest or smallest value of the objective function is called the optimal value, and the pair of value of x and y that gives the optimal value constitutes an optimal solution.
In mathematical optimization, the fundamental theorem of linear programming states in a weak formulation that the maxima and minima of linear function over a convex polygonal region occur at the region's corners. Further, if an extreme value occurs at two corners, then it must also occur everywhere on the line segment between them. The fundamental theorem of linear programming states the following. 1. The problem is infeasible. 2. The problem is unbounded. Or 3. The problem has an optimal solution. For any given linear programming problem, exactly one of the following must hold. We're going to prove this theorem by showing that if the problem is not infeasible and is not unbounded, then the problem has an optimal solution.
Solving a linear programming problem graphically. 1. Define the variables to be optimized. The question asks a good indicator as to what this will be. 2. Write the objective function in words, then convert to mathematical equation. 3. Write the constraints in words, then convert to mathematical inequalities. 4. Graph the constraints as equations.
Number 5. Shade the feasible regions by taking into account the inequality signs and its direction if a. Vertical line greater than then shade to the left, less than shade to the right. B. A horizontal line greater than shade to below, left than shade above. C. A line with a non-zero defined slope greater than shade below, less than shade above. Number 6. Identify the corner points by solving systems of linear equations whose intersections represent a corner point. Number 7. Test all corner points in the object function. The winning point is the point that optimizes the objective functions biggest if maximizing, smallest if minimizing.
Now let's calculate the value of x. 10x plus 20 times 0 is equals to 120. Since 20 times 0 is 0, the answer is 10x is equals to 120. We're going to divide it by 10. 120 divided by 10 is 12, so the maximum value of x is 12. Sample number 1 is maximize j equals 12x plus 16y, which is the objective function. We call this objective function because it has two variables. While the constraints is 10x plus 20y is less than to 120. We're going to solve the 10x plus 20y is less than to 120. Since x and y are equivalent to 0, we're going to replace the x to 0. So 10 times 0 plus 20y is equals to 120. 10 times 0 is 0, so we're going to bring down the 20y is equals to 120. And if we divide it to 20, the maximum value of y is 6.
Solving the linear programming problem using simplex method. Example 1. Consider the following standard maximum type linear programming problem. Step 1. Insert slack variables. Insert a slack variables into each of the structural constraints. The result is this system of slack equations. Step 2. Rewrite the objective function. Rewrite the objective function to match the format of the slack equations and add the corresponding equation to the bottom of the slack equations.
Step number 3. Write the initial simplex W. The augmented matrix is called the initial simplex W. Each number in the bottom row to the left of the vertical bar is called an indicator. Step number 4. Find the 5-vote element. The most negative indicator in the last row of the W determines the 5-vote column. We apply the smallest quotient rule for the column. Find the 5-vote element of our initial simplex W below.
Step 5. Perform the 5-vote operation. Perform the 5-vote operation to find the 5-vote element. After the 5-vote operation has been completed, write down the basic feasible solution. Step 6. Check if there are still negative values in the third row. If a negative indicator is still present, repeat steps 4 and 5. If no negative indicators are present, the maximum of the objective function has been reached.